This will be a mixture of things. I told you I will start with stochastic processes, but there were things I didn't finish from the previous lecture on times and rates. So I first continue with time and rates. Continuation. Won't be long. Something I found curious from the book, in the reference that I gave you, is a number about speed, which is the example of a bacterium, which is, for example, E. coli. As I told you, it has a body of the size, of around 1 micron, and it swims in a fluid environment. It can swim in water, for instance, powered by some legs that are called the flagella, which are these ones. Okay. Each of these is called a flagellum, and in plural is called flagella. So, interesting concept in the motion of bacteria is that this motion is not like rectilinear. It's not like moving in a very regular fashion, but bacteria often encounter obstacles, so they should be able to turn and swim in any direction. And this they do thanks to these flagella, which are not just simple legs, but these are powered by motors that are located in the membrane of the E. coli body itself. These motors have the following shape. So if I zoom in this region, I would see that this will be the body of the cell with the membrane. And on top of that, there is a structure that has the shape of cylinders stacked one on top of the other, from which the flagella starts to, it's stuck to these cylinders. So the flagella, this is a flagellum here, and this has a mechanism of rotation. So this you can think as a wheel. You put like a rope in the wheel, and the wheel rotates. This wheel can rotate in different directions. Of course, this is an active process, so it is not just a fluctuation, but there is fuel that the bacteria can use, like ATP, to move this flagellum. And this rotates, and the question that, okay, first of all, I didn't tell you about the size. This is obviously smaller than 1 micron. This is of size of nanometers. So it has a diameter of around 40 nanometers. So it's a very, very, very small wheel, and the frequency of rotation, in rotary molecular motors. This is, okay, rotary means it performs rotations. It's of the order of 100 turns per second. So this wheel is spinning at a rate that is of the order of 100 turns per second. If you think about it, you can transform seconds in minutes by this simple relation. So 1 minute is 60 seconds. So this becomes 6,000 turns per minute, which, if you like cars, this is often called RPM, revolutions per minute. Okay. This is still the first part of the course, in which I'm relating this to engines and things of common life. So 6,000 revolutions per minute. So simple question is this fast or this is slow compared to the engine of a car, for example.
It's almost like a car.
It's almost like a car. Yeah, good point. So if you find online, for example, a Ferrari car, for example, this one.
It's like a turbojet, I think.
Huh?
At 6,000 RPM, it's like a turbojet.
Yeah. So Ferrari, for example, is 7500 RPM. It's like a turbojet. It's really fast. However, it's not that you are doing turns. You're doing turns of a very small wheel. So this should cost you less energy than switching on the engine of a Ferrari. So in a Ferrari, the power is around 500 kilowatts. This is the power of a fast car, let's say. However, the power of this motor in power of the rotary motor in equali is of which order do you think is the power? I tell you, car can make these rotations, but the energy expenditure is very high. What about the motor? How many watts do you expect? Yeah, little, but you should know a number. This lecture is about this. It's about knowing orders of magnitude. Do you remember in my previous lectures, I talked about watts at some point?
Yes.
And what was the order of magnitude I was talking about? Electron volt? No, that's charge. That's energy actually. Watt is energy per unit time, per second. So when you don't know, you can think about it in terms of the biological units. So you will use kVts per second. In this case, it uses around 1000 kVts per second. This machine uses 1000 kVts per second. What it won't happen is that there will be millions of kVts per second. This makes no sense. Or 0.00001 kVts per second. No. Also, this is very, very strange. In biology, typically, everything wastes around 1 kVt per second or more. But not millions of kVts per second. That's very common for something so small. Okay, this is the order of magnitude, and you can convince yourself, and this you could do by looking at your previous notes. You can pass these to watts, and you get around 1 attowatt. This is 10 to the minus 18, attowatt. Remember? This is attowatt. And this is 10 to the minus 18 watts. So, what you see, remember this is kilowatts, so this is 10 to the 3 watts. So this is 5 times 10 to the 5 watts. This is 10 to the minus 18. Very, very much smaller than this one. So you have an engine is equally fast as the Ferrari in terms of revolutions per minute, but it spends much less power because it's moving a smaller wheel in the end. So it makes sense. For reference, I gave you just one here, but I can give you a table. So you can check this nice book, which is by Howard. This is a book on mechanics of cytoskeleton. And molecular motors. This book is very good for you to learn about what are motors, what is motion in biology, also what is the cytoskeleton of the cell. And in particular, there is a very nice table which gives data about motors, their speed, their power, and their function. And I give you some examples here, different motors in biology. the function their speed in nanometers per second. Remember, you can pass this number to nanometers per second because you know the period of the wheel. So you know it makes 100 turns per second, and I give you the diameter. So if it's a circle, you know the diameter, 40 nanometers, it's making 100 loops per second. So you can pass this to nanometers because you know that the perimeter is 2 pi r. So it's 2 pi times 40 divided by 2. This is the radius. So this will be 20 pi nanometers. No, 20 pi because it's 40 divided by 2.
Yeah, it's 40 pi.
40 pi, 40 pi. Good. You are paying attention. 40 pi, which is around 120 nanometers. Okay. This is okay. This is one turn. It's making 100 turns per second, which means it's traveling. Okay, so the distance traveled will be this times this. Okay, so if you put a particle here and you look at its motion, the distance traveled by this particle will be 120 times 100 nanometers. Okay, that's very easy. Okay, that's why I give you speed in nanometers per second. Also because the motors that I'm going to give you here are linear motors. Motors that move in a line, not in a circle. Okay. Secondly, I can give you also the ATP rate to give you an idea of these numbers. One example is myosin 5. Myosin 5. Okay, this 5 means there are at least other 4. So myosin is a family of motors, and each of them has a different structure and function. This one, the function is vesicle transport. The speed is around 200 nanometers per second, and it consumes 5 ATPs per second. All these are estimates, but you can also go to the lab and measure this with a very good microscope or other techniques. Another one is dynein, which is involved in mitosis or flagellar transport. It makes 1000 nanometers per second and spending 2 ATPs per second. So you see, some motors are faster despite they spend less energy. So it's not all about, there's not a linear relation between the fuel consumption and speed, but it's more complicated because the motors can have different structure, different weights, different friction, etc.
Excuse me, the second one name is
Dynein.
dynein, and its function is
Mitosis is involved in mitosis and flagellar transport. Okay, you can look for it in the book. Another one is kinesin. We take here conventional. This is the name of the motor. Kinesin. This is involved in axonal transport, transporting axons in neurons. It makes around 1800 nanometers per second using 40 ATPs per second. Here I give you 3, but if you go to this book, you will find 20 or 30 of them. So now they are much better known than before. and this can be measured very well in an experiment. I'll send you also a video of molecular motors, which is it's an illustration, but it's very spectacular. So you see how they work, what they do. But this is just an introduction. And I go to the last part, okay, for which I need some space. Here will be fine. Alright, so the last will be about rates, about which I didn't say much. And for rates, to discuss briefly rates of chemical reactions. So I'll think about the following setup. Imagine you have a container which has two species of molecules, X and Y. Y, X, Y, X, X, Y. And there are chemical reactions happening in this container. So X can become a Y, and also Y can become an X. And this happens at a given rate. The rate, I call it K. K, I can call it K X to Y, and K Y to X. Rates will be very important in my course later. So what you need to know is rate means transitions per unit time. So how many times the transition X to Y happens per unit of time. So I have 1 second, and in 1 second, on average, how many times do I see X transforming into Y? Of course, the chemical reactions are stochastic. You put many X and many Y's, and they are making the reaction at random times. But this is about averages. I look at many, I count how long it takes to become Y, and I divide. Well, this is the inverse of the time. It's 1 divided by the time needed to become Y. Okay. One key concept in this process is equilibrium. So when do you reach equilibrium between these two species? And there is a condition of equilibrium which is called Dieter balance, which maybe you hear about. Dieter balance, which is the following. It's a relation between these two rates. The rate in going from X to Y and the rate in going Y to X. In equilibrium, these two rates are related by a Boltzmann factor. Okay. And now the question is, what is T? Well, T is simple. So this is in a thermal bath at temperature T. This is the temperature. Now the question, okay, Kb is simple. Kb is the Boltzmann constant. And what is delta S? This is an important question. You want to guess?
It's the energy difference from state 1 to state 2.
Is there any difference between state 1 and state 2? But to give you a picture, a physical picture of this is the following. I will draw here the free energy of the chemical reaction, and this will be the reaction coordinate. Reaction coordinate. And plot in this diagram what is called the free energy landscape. This is the free energy landscape in going from X to Y. This is something we kind of a physical representation of this process, in which we think one molecule, that is X, is here, and now it's like diffusing in this sort of potential, and it becomes Y when it arrives here. Okay? When you have this picture, this is very useful to understand this, because these rates means that if you put many particles in X, you let them evolve, they don't look at each other. Kxy would be the average number of particles that arrive to y per unit of time. So, for example, you say, I put my clock up to 1 second, and I look how many, I put 1,000 particles here, and I count how many of them reach y in this interval of time. If there are 3 that reach out of, I don't know, 1 million, this will be 3 per second. Okay, this is the idea. So, how do you reach here? So, this comes from what is called the Arrhenius law in chemistry, which tells that k from x to y is a prefactor times E minus EA x to y divided by kd. Okay, and what is, well, okay, this is a rate, a nu. It has units of 1 over time, and this is called the activation energy. Okay, I call it EA. This is the activation energy. What is the activation energy? So I go from x to y. What do you think is activation energy here? Activation energy, if you think about the word, is energy to get activated, so you reach the other place. Activation energy from x to y is this distance. This is EA x to y. So you have to think like a ball rolling in the potential, how much energy you have to give to the ball such that it reaches y. If you forget that there are fluctuations, if the ball gets this energy, it will come here and then roll down. This is what is the activation energy in this picture. Okay? So the rate in going from x to y depends on this energy difference between this state and this state. Whereas if we go backwards from y to x, you will need this energy to reach the top of the mountain. So k, y to x is nu E minus EA y to x divided by kd. Right? So in this energy landscape, it will be much easier to do x to y than y to x, because the mountain is higher from x. Sorry, the mountain is higher from y than from x. Now, if you do the ratio, k x to y, k y to x, these two cancel each other, and you get E minus EA x to y minus EA y to x divided by kdt. So what we get here is this height minus this height. So what remains when you do this is the distance.
Sorry, Professor. We can.
Sorry?
That we can see it very well. We can't.
It's very small.
Yes, very small.
Yes, and what can you see the formulas?
No.
Okay. Fine. So I'll write it again here. We'll do a zooming version of this. Right, because
Excuse me, what's that sign before E? And we cancel out.
okay, let me do it again. Okay, this is the free energy. This is the reaction coordinate. And then we have this energy landscape. This is state x, and this is state y. So this distance here, it is the activation energy x to y, and this is this, and from y to x, the activation energy is this one. Activation energy is the energy in the maximum minus the energy in the minimum. So the energy I need from x to climb the barrier. Here, this will be the activation energy, E8 y to x. And what I said before is that Arrhenius law, this is Arrhenius law, tells you that k x to y is rate e to the minus E8 xy divided by activity, whereas k y to x is nu e minus E8 y to x divided by activity. Okay? You see this more clear?
Yes.
Good. So if I take the ratio k x to y divided by k y to x, these two are cancelling, and what I get is e minus E8 x to y minus E8 y to x divided by kbt. And this, so I'm doing this distance minus this distance. So what I get is this one, which I call delta E. So it's the energy difference between the two minima. So the difference of energy of state y and state x. This is what I call delta E. So this is E minus delta E divided by Q. Right? So it's the energy of state x minus the energy of the state y. Right? This means that if delta E is positive, sorry, this is incorrect, this should be plus delta E, and this is Ex minus Ey. Okay? This way. Yes, as I said here. Okay? Plus delta E. So when delta is positive, it means the energy of x is higher than the energy of y. We will get transitions in this direction. And this format tells us this. When delta is positive, this is positive, this is greater than 1, so this is greater than this. Okay? K x to y greater than k y to x. And when we get the opposite, it will be the opposite. K x to y smaller than k y to x.
Here and K is possibility,
Transition rate.
transition rate.
Transition rate. Or reaction rate.
And mu is what? What's the mu?
It's also a rate.
Rate.
Rate parameter. It's called.
Okay.
K is a transition rate. They will come in the course later. Rate or chemical reaction rate. Reaction rate. Typically it is given in seconds minus 1, etc. How many times the reaction happens per second? Okay. So, interesting question here, now I will be back here, is what happens, okay, it's clear what happens when I change the activation energy, more or less. What is not so clear is the role of temperature. More or less you see it here, but let me give you an example on how the rate depends on the temperature, which is not so trivial, as you'll see. So, given this, first of all, I'll give you numbers for the activation energy. So, what's the value of EA in biological processes. I'll give you some examples. One is transport in ion channels. Remember, in the ion channel, what I explained in my previous lectures was there are two configurations, open and close, and this has also an associated activation energy. So in this case, the activation energy is of the order of 8 cavities, which is most commonly written like this, kilojoules per mole. Remember, in the first lecture or second, I told you you can convert kilojoules mole to cavity. It's not that difficult. If you go to biochemistry books, you will see this. This is more what we do in physics, cavity. If you look at other, like enzymatic reactions, so an enzyme that takes one product and transforms it in a, reactants and products, takes a reactant and transforms into product. This has also this type of behavior, and in enzymatic reactions, we have activation energies the order of 10 to 20 cavities. They are higher. This leads me to discuss the dependency on the temperature T, which is an important question. So imagine I have an enzyme in a glass of water. This is temperature T, and now I want to know what happens if the temperature increases 10 Celsius degrees, for example. This will change everything here. The T will change, so transitions in one direction and in the other will change because of the temperature. So I can ask, for example, how much does it change the rate when I am in a temperature that is T plus 10 degrees with respect to the room temperature. Okay, so this will be the rate at temperature T, x to y. This will be the rate x to y at a higher temperature. This is a temperature T prime, which is the room temperature plus 10 Kelvin. Imagine I ask you, okay, how much is accelerated a reaction when I have 10 degrees more? And this is very simple because you have this formula. You just have to do this at T and this at T plus 10. That's it. If I tell you 10 Celsius degrees, it's the same as 10 Kelvin in a difference of temperature. Okay? It's not the same temperature. So 0 Celsius is 273 kelvins, but a difference in temperature of 1 Celsius is a difference in temperature of 1 Kelvin. So the only difference between the two scales is the 0. Where is the 0? I don't know if you remember this. So what I mean is that this is 0 Celsius degrees, this is 1 Celsius degrees, this is temperature in Celsius, and temperature in kelvins. It starts at 273 kelvins, but 274 is here. Okay? I hope you remember this.
Yes.
So the point is that 0 kelvins is minus 273 Celsius. The only thing that changes is the origin of the scale, but the accuracy of the scale is the same. If we increase this room temperature 1 Celsius is the same as saying 1 Kelvin. This is important for this. And you see it because when you do the calculation, in one case you will have T, and the other you have T plus 10 Kelvin. But it will be plus 10, but then the T you have to put is the Kelvin temperature, not put the Celsius. Okay? So when you do this calculation, the nulls cancel, and the only thing that remains is, can show you what it remains, is e to the minus EA, KB T plus 10, Kelvin, e to the EA, KB T. Okay? This is it. One goes numerator, the other denominator. That's why one has a minus, one has a plus. There is a plus 10. And here in T, you must put the room temperature, which will be, I don't know, around 300 Kelvin. Room temperature typically, this T we take usually 300 Kelvin. Okay, 25 degrees for us. 25 degrees Celsius. You see that this number will depend on EA as well. So if I do this ratio of rates, I get, for this example, let me call it A and this B. For A, I get, 1 second, I get 1.3. For A, I get that the rate is accelerated, 1.3. And for B, I get around 2. Okay? So in one case, the rate at 10 degrees more is 1.3 times the rate at the same temperature. So this means I increase it 30%. In the other case, it's twice. So the rate at 10 degrees more, the reaction happens twice faster. Just by increasing 10 degrees of temperature. Twice faster. So it's not linear. This is the main point. If I then go to higher temperatures, this will increase much more. Okay. So I think this is simple. With this, I finish this part of estimates. So if you have any question, it's a good moment to ask. Do you remind this from your chemistry lectures, physics, the Arrhenius law, that one? You don't? Okay. Of course, this is not universal. This doesn't work for all temperatures, etc. This has a range of validity. But biological systems, you can be in this range where this is valid. Okay, so I'll do a break and start the next block on stochastic process. But I think, okay, let me do 5 minutes. I'll try to finish around 4 today. Okay. I do a small pause. I'll continue the recording. So now I start a new block on stochastic process. Which will be several lectures. My first thing I will do is to give you definitions so we can understand each other. It is very important that you understand the math I use, but also the symbols and the notations. So the first thing will be definitions. Introduction. And generic properties. Generic means properties that are common to all stochastic processes. So this will be a bit formal, but quite useful. You'll figure out. First thing I'll do is, well, I think I already already introduced you stochastic process, but I will reintroduce by doing a comparison between a deterministic and a stochastic process. So this will be here, I will plot one example of a deterministic process, which is defined by an initial condition, x0, and by some laws of physics that determine the evolution of this process. In general, this process will evolve smoothly in time. So we will know at any, this time will be time 0, we will know at any time t prime with certainty where will the physical system be. This will be at a given position and then continue. Okay? This is the so-called deterministic process. Deterministic process, which is, for example, a process described by the laws of mechanics. When you have the laws of mechanics, Hamiltonian equations, these are deterministic equations. So if you know the initial condition, you know the equations that govern this physical system, you will know the future with certainty. The laws of Newton, well, you know the laws of Newton, the initial condition, you know the future. So they are often described by differential equations. Differential equations, which you had a nice introduction. For example, ODE. For example, this is not the only one. Ordinary differential equations, such as x dot equals f xt. This is an ordinary differential equation. F xt can be anything, and x of 0 equals to 0. This is one example. But you could have many other equations here. As you see, the characteristic is, in an ODE, first order differential equation, you only need, okay, you need to solve the equation, but you just need to know what is the initial position to know the future. In contrast, what we will describe now is different in nature in the following way. So, one good example of stochastic process is if I flip a coin. So if I flip a coin and I register if I have heads or tails, this will be a process which has two values, heads and tails. And this will be kind of random motion. So what will happen now is I have x0, but now the future is not fully given. It depends on noise. So I can integrate the equations of this process, follow the physical laws, and then at a given time, t prime, I could be here, but if I do the process again with the same laws of physics, I could be also here and anywhere else. So there is uncertainty, there are fluctuations. This is called the stochastic process. Different nature than the deterministic, and they are described by other types of equations that I will teach you in this class, which are the stochastic differential equations, which will be given to you in some examples, and also probability theory. Probability theory will be important because you must think that now, if you look at a given time, there is fluctuations, so there is a probability distribution for the system. Here we have a probability distribution for the system to be at x at time t. Okay, this means that at a given time t, there is a probability to be here, but there is also a probability to be here, and a different probability to be somewhere. So this will be a very important object in the study of stochastic process. As I said, here, good examples for deterministic process were the laws of mechanics, the laws of classical mechanics. All that you learn in high school, in university about classical mechanics is deterministic motion. However, this is not enough to describe other phenomena in physics, such as stock market, for example, or finance, such as gambling, such as running motion, finance, and climate, etc. So it has many applications, as you will see. Of course, stock market, I won't teach you this, but I could give you an appetizer and some simple applications. Gambling, running motion, I think makes sense. An example of stochastic differential equation, which is often called SDE, stochastic differential equation, would be something similar to here, with an initial position set to 0. Not always the initial position will be 0, right? Remember.
Excuse me, what's SDE?
Stochastic differential equation.
And what are those stochastic differential equations are?
This is the question I will try to solve in my
You are
method. I will give you
introduced.
definitions and I will show you how to do stochastic calculus, because now there will be a different way of doing calculus. It won't be differentials and integrals as you did in the university. It's different.
Because I was wondering, when we are speaking about the equation, it means we have a function that everything is inside and you can understand, you can have input and output.
Yeah.
So everything is deterministic,
But now it's not. So even if you want to do
that
it,
means a stochastic.
yeah, even if you think about this, I tell you calculate the area under the curve. It doesn't matter how you do it with Riemann partitions, you will get always the same result. If you want to do the integral of this process, it depends strongly on how you do it, and you will get a different result. If you do partitions in one way, I do another, we will get different results. This you will see in 2 or 3 lectures, you will see it. Okay? Different ways of taking derivatives, different ways of doing integrals. So here, what we use is standard calculus. For example, making the chain rule in the derivative. The derivative of, I don't know, what you know the chain rule is like. Here the chain rule is different. Here you have stochastic calculus. Which will be probably the first time you get into this, it will be my course. But then it's math, it's useful for you, you will see. So one example of a stochastic differential equation will be something like this, fxt plus xi of t. And this, we call it noise. So the equation will have a term in the derivative that will be random. This will be like a random number in any step. It's one example, but as I say, there will be many that will come. This is just to motivate what is coming later. Right. So, what would be the most trivial example I can think about? Will be coin flipping. Example in gambling will be a coin. So you have a coin, and you can have two values, heads, that equal -1, and tails, that they give 1. So I have a process in which every time I flip a coin. If it's heads, I give the value minus 1, and if it fails, I give the value 1. So this process will look like this. This is t. Time is discrete in this case. So every time step is one flipping, and it could be, I don't know, minus 1, and 1, minus 1, minus 1, minus 1, 1. It would be something like this. Okay. It's the simplest, but another one that is quite paradigmatic that you will appreciate to learn. It is the discrete random walk. So very good example. Let me write here. Here. Very good example of stochastic process. It is quite easy to do calculations. Example is the discrete time random walk. Discrete time random walk. I already talked you about diffusion. So this is like a diffusion but in discrete time. And let me give you a definition of how we build it. So time 0, so discrete time means that time takes the values 0, 1, 2, etc. Remember, discrete, so the time can be discrete or continuous, and x, the state, can be discrete or continuous. Okay, so I will try to be precise. If sometimes I don't say it, ask me, and I'll let you know. But there are different processes that are important, that are in discrete time or in the continuous time. This one it has a pedagogical value. It's good for you to learn. It's in discrete time, and also space is discrete. So t is discrete, and x is in z. Okay, you can take values minus 1, plus 1, integer numbers. It is defined as follows: at time 0, we are in 0. At time 1, we are in x0, which is 0, plus a noise increment, xi1. So what is xi1? Xi1 is plus 1 or minus 1. So it's a random variable. This is a random variable. This is not random because it's the previous step. But it's random. It's plus 1 with probability 1/2 and minus 1 with probability 1/2. Okay? So I can do a drawing of what is going on. So again, I'm flipping the axis. This is x. No, sorry, this is t. T is going up. This is x. So time 0 is here. There is time 1, time 2, time 3, time 4. At time 0, I was in 0. At time 1, I can go to plus 1 or minus 1. So I can go to plus 1 or minus 1. So either here or here. Okay? Time 2, I will go to x1, so the previous position, plus, again, a noise. And the noise will be given by the same type of variable. This will be the same type. So if I am in 1, I will do 1 plus 1, I will go to 2, with probability 1/2, or 1 minus 1, which is 0, with probability 1/2. So every step has a probability 1/2 and 1/2. If I was in x1 minus 1, I will go like this, or like this. Okay? You see, this is branching like a tree. Okay. Time 0, I am in 0. Time 1, either I jump, I will be x0 plus xi1. Xi1 is a coin that you flip.
You will move one step here.
Yeah.
And in which direction
it's random, so either +1 or -1. So you could go here or here, okay?
You're moving in a direction that is not completely 1 meter, for example.
You don't have to move 1 meter.
And I don't know.
You do steps of size 1, and either to the right or to the left. And
Yeah,
this depends on chance.
Yeah, but it's not right, not left. You're going diagonal.
You could go diagonal. You could.
If you can go anywhere, it's you will have a circle for probable.
No, but you cannot go anywhere because the jumps are only +1 or -1.
It's only one dimension.
One
Yeah.
time motion
In
will
one-
have probability, it's either heads or tails.
I see, but
Okay, maybe discuss it. I'm drawing here all the possibilities, all the possible paths.
excuse me, you're drawing XY time. I see.
This is
And
T
now
and this
I
is X.
understand. Yeah,
Okay?
okay.
Okay, this is to link with the previous lecture where I draw the trajectories where they were expanding, okay, in the diffusion. One trajectory will be like this. This will be one trajectory. But another one could be like this. Okay? These are different trajectories of the
The
particle.
problem was that I thought that that's y-axis, not the t.
I thought, be careful what I write here and what I write here.
Yeah.
This is not a typical representation, but I think it's useful.
Yeah.
I think it's useful. Also to connect with the previous lecture. Typically people plot them like this. But we have some freedom to do, no? Okay. I'm plotting it vertical, t and x. Okay, so this generates a sort of tree, because then I do x3 will be x2 plus psi 3. And so on and so on and so on. So I'm here, from here, these 3 points, I could go or here, or here, or like this, or like this, or like this. All the jumps are with probability 1/2. 1. Okay. Is there a question?
I think we use this in economics.
In what?
Yeah, in time series regression.
Time series regression. Okay,
Yeah.
probably. So
This stuff.
something you see here is that x2 is x1 plus xi2 and x1 is xi1. So in reality you can write x3 like, well, you can do a cursive and find that x at time t is the sum from s equals 0 to t of psi s. That's it. You are summing +1 minus 1 up to time t. Be careful, this is random. So if Said makes one simulation, he will get some numbers. But if I do, I will get other numbers. So this is random. This is the most important thing, that this is random. A random variable, okay? Random variable. Another important point is that at S0, so I'm saying this is psi t for any t greater than 0, but psi 0, I set it to 0. Okay? And this is the definition of the random walk.
Yeah.
Which tells you that we can do calculations, we can learn, for instance, this should be clearly direct to you to learn what is the average of all the paths. You remember, this is related to diffusion. The average would be 0. If here I would put a different probability, for example, 2/3 to the left, 1/3 to the right, there will be a drift.
Either downward or an upward.
Either this way or this way.
Okay.
That would be if I would get, for example, here 2/3 and here 1/3. If I repeat the tree with this, I will get a drift. This is random walk. The other one would be the biased random walk. It would be a bias. Okay. Just as a comment. But given the formula and the statistical laws, you can ask yourself what is the average at time t. And well, once you have the formula, you just go on. So s equals 0 to t of psi s. And what do we do? This is, okay, I saw Mateo's lecture. This is what he calls E, expected.
Yes, errors.
Okay, I use this in physics. This is more common, I think, than E,
Yeah,
expected value.
variations, yeah.
So, what is this? What can I do with this? Well, these xi's are independent. So I can take the sum out and make the average inside. And now the question is, what is average psi? Yes? 0. The average of this is 0. So sum of zeros, 0. 0. Fine. No drift. There will be a drift, there will be something times t. And now the next question is the variance. What is? Okay, the variance in this case. Remember, the variance is xt squared minus xt average squared. The average of the square minus the square of the average, the variance. This is 0. The average is 0, the square of the average is 0. So we just get xt squared. And now we must do this calculation. So should be easy. This is just the sum s equals 0. Psi s to the square. Okay? Okay, what is this? So it's a sum of squares. It's a long sum to the square. So you have a plus b squared, it's a squared plus b squared plus 2ab. Now you have many. So you should use the binomial formula.
I'm sorry?
Binomial formula.
Yeah.
But, just think about one thing. These xi's are independent. So there will be many terms that will be xi, for example, xi1 squared, xi2 squared. These they will appear. But there will be also xi1 times xi2. That's 0. That's it. Okay, so psi, I don't know, how can I call it? Psi t prime is equal to 0 when t is different to t prime.
Yeah.
Because they are independent. You get this?
Understand
Yes.
Okay, psi t times psi t prime. When there is statistical independence, this is psi t prime. And each of them is 0. You know, if t is different than t prime, if it is the same, it is not. If t is equal to t prime, we will have psi t squared. Okay? And psi t squared, 1. This is 1 because I will have plus 1 with probability 1/2 minus 1 probability 1/2. So it will be 1/2 times 1 squared plus 1/2 times minus 1 squared. So this is 1/2 plus 1/2 is 1. And that's it. That's it. This is square is 1.
What's the last line? What did you do?
So I calculated psi squared average. Psi can have two values, 1 and minus 1.
Yeah.
Psi squared can only
It's
is
always one. Yeah.
is 1 squared and minus 1 squared, each with probability 1/2. So it's 1/2 plus 1. 1. So all in all, here we will get sum psi square from s equals 0 to t. So we will sum 1 t times. Remember, we are summing from s equals 0 to t. S equals 0 to t, it has t plus 1 terms. T plus 1, but the first is 0. So in reality we have t terms that are not 0. And they are all 1. So this is t. T. So here we got the law of diffusion, which I gave you the other day. Xt squared equals to t. Right? This is a Brownian particle with diffusion 1/2. Remember the other day I told you 2 dt.
Yeah.
This is a Brownian particle with diffusion 1/2. It's the same model in discrete, but with a given value of the t. And next thing, these are the main properties of the random walk. Average, zero average, and the variance increases linearly with time. And of course, this comes from a physical model. We can generalize this to 2 dt. This is square t. Well, dt with t equals 1/2. This is the physical model for the random. Right. So, okay, I think this is a good example to start, but they will become more and more complicated. Something that it will come later is the type of stochastic process. This is called IID, independent identically distributed process. It's called the IID process. And this one has a different name. Very important for you to know, which is a Markov process. This is a class of processes that contains this as an example. Okay? Markov process is a type of stochastic process. And this is one example of them. IID process is also a class of stochastic process, and this is one example. As you will see later in my course, the Markov processes are extremely important in physics. There's a lot of research now. I also do research in Markov process. Many people in the world, and they are very much used in biophysics. So it's very important that you get to know about their properties. So,
Are these the same thing?
sorry?
Isn't it the same exactly?
Sorry?
Isn't this the same example? Oh, no, okay, so that is the... Okay.
Markov process, this is one example.
No, I get it.
IID process, this is one example.
Okay.
But I will be more rigorous later in the course. Alright, so having said this, I'll go a bit on definitions so you understand what comes later, and some general properties. One thing that we also will discuss is a bit of numerics and how to do simulations with a computer of this process. This, I think, will be good for you to visualize things. So, I go now to generic properties and definitions. Generic properties and definitions. And I will follow the book, very famous book of Van Kampen, which I highly recommend you to read. Van Kampen on stochastic processes. So, first of all, let me define what is xt. There will be big X and small x. This is big X. This is the value at time t of the process. value at time t. The process could, I'm showing you until now one-dimensional, but there could be many dimensions. So when there are many dimensions, I will call it x mu t, with mu equals 1, 2, 3, for example. This is when there are many dimensions. This is when it's 1t. So by now, let me write everything 1D because it's simpler. I will also define pxt, and now this x is small, which is the probability density for xt to be equal to small x. Okay, probability density. Density at time t. And as I said, xt will be the average of the process at time t. How do I? Okay, before I was being very short with notation, but this you can define it mathematically. So if x is continuous, this is given by this integral. Okay, is the integral of x. This is the density. Remember, density has unit of 1 over x times x has no units, and then times x has units of x. Makes sense. If x is discrete, this is done differently. Okay. This is for continuous. If it's discrete, this will be summation p xt times x. And x will be discrete, so this will be over i's. This is for discrete. This is for x discrete. And this is for continuous. Okay. In this case, this is a probability. In this case, this is a probability density. Nothing else than that. Okay, and of course, the integral will go differently to different process. If I have a random walk, this will be from minus infinity to plus infinity. But if I have a random walk in front of a wall, the particle cannot cross the wall, then I have to integrate only on the accessible space. Okay, this is very important. That's why I don't write it here. Different problems and different integration domains. All right, this is the mean or average at time t. I will use both words, the mean, the average. I will be changing. Of course, this can be generalized, so you could have x to the power n t. Okay, this will be the moment, the n order moment. I was talking about x squared, but you can think about x3, x3. So, this is fine?
Yes.
Okay. So, one key goal for me will be, let's say I have stochastic process and these are the definitions. A key goal would be to understand statistics of the process. Would be statistics, and one of the biggest thing I could achieve would be to compute statistics of trajectories, which is the following. You have the process x versus t, and I would like to know in particular, this is stochastic, I'd like to know, for example, what is the probability to see this trajectory. Here I'm telling you what is the probability at time t, at a given time, to be somewhere. But I would like to be more ambitious and know, for example, what's the probability of all this that the process produce an entire trajectory. For this, there are notations that I will introduce. So this will be, for example, T1, and this will be x1. Small x is the value of the trajectory. No, sorry. It's not good. This is x at T1. Big X at T1 is the value of x at time T1. Then big X at T2 will be the value of x at time T2. And T3 can be anything, and we put it here, T3. And this is x at time T3. So, I define here P of x1, comma T1, semicolon x2, comma T2, semicolon, dots, semicolon, xn, tn, small x, this will be the equal to the probability density that the system is at T1 in x1, at T2 in x2, and at Tn in xn. So here, this object has to be understood as the probability that the system is at small x1 in time T1, at the small x2 in T2, and the small xn in Tn, in this way. Okay. This is called the path probability. And remember one thing, these t's could be whatever. They don't need to be equally spaced. Sometimes they will be equally spaced in my course, but some others, no. Okay? They just obey that T1 is smaller or equal than T2, more or equal than Tn. That's it.
What it means T1 less than or T2?
It means that when I write something like this time is more than this and more than this. So I'm writing like this. Okay?
You cannot
Just
go past to go.
I could, but I don't want to mess it up. I just want to be organized and do it like this.
Okay.
Right? Okay, so I'm almost done. I will just discuss something very mathematical that are generic properties of stochastic process, and these are due to Kolmogorov. Kolmogorov is the father of probability theory. So you may hear from him many times during your diploma. Kolmogorov. Basically, Kolmogorov found that there are three conditions that need to be satisfied in order to define uniquely a stochastic process. The conditions are as follows. So any stochastic process, any like IAB, Markov, or whatever stochastic process, has to obey these three conditions. The first is a bit obvious, okay, which is the following. Let's say this defines stochastic process, the probability of a trajectory. Okay, without telling you the dynamics, if I give you this function, you could tell me if this is stochastic process or not, if it follows this. Okay, the first is P should be positive. Okay, you say how stupid is this, no? But yeah, it's a bit mathematical, but the probability to see any trajectory is greater or equal than 0. So equal is included. If you have a Brownian particle against the wall, there is probability 0 that the Brownian particle passes the wall. It's greater or equal than 0. Fine. The second is the so-called marginalization property. Marginalization, which is the following. I take the probability of a trajectory and I integrate it over one variable. For example, xn. P x1, t1, x2, t2, xn, tn. So I'm integrating this probability over xn. What should I get if things are all fine?
What is this mean? Marginalization?
It means what I'm going to write now. So I'm having a probability density
You're
of,
normalizing it, it should be one.
be careful, these t's, they don't play a role in this average because they are not stochastic.
Yeah.
These are just indices. So in the end you have this is a density of n variables, 1, 2, up to n.
So n.
There are n variables here. Very important you to keep this in mind. This is a density of n variables, n random variables here. One stochastic process, and I'm taking on it n random variables. N could be 1, could be 5, could be 1 million or 1 trillion. Okay, I'm taking n points. So if I sum over 1,
But it's still a probability, right?
it's still a probability because the rest keep to be random.
Yeah.
So this is what is called marginalization because I'm marginalizing. I am taking one of them and integrating.
Yeah.
But the rest are still there. So this becomes P of x1, t1, x2, t2, up to
X and
xn minus 1, t n minus 1. Okay, very important. Here, I reach n, and I'm integrating over this. This is not random, tn. Now, when I integrate only that one, I keep with a new distribution that has n minus 1. Here there are n minus 1 random variables. And here there are n random variables. Okay?
So you're fixing other variables and integrating over one,
Yes.
and we will have.
It's like if I do this. I have two variables x, y. I integrate over x. Then I still get y. Okay. But if I have 3, I still have 2 that are free. Okay. But I could do this way. dy d x, y, z. If I integrate over y, I should keep only x and z. Okay? You don't see it? Okay. Here I'm integrating over x. I have x, y, z. This is the variable that should disappear because I'm integrating over this. So out of...
integration, it shouldn't disappear. In differentiation, it should disappear.
Sorry?
But
Can you repeat?
no, it's nothing. It's just.
Okay, here I have x, y, z. I integrate over y. So this has to disappear on the right side. So I get p of xz. Okay, remember this is a simplification. I think this is better
Yeah.
because it's a different t's. This is a bit of an illustration, but okay, maybe if you want more precise, this should be x at t1, y at t2, and t3. So the t's should come with them in this way. I think this is the clear. You can convince yourself by taking examples and do. For example, you put x t1, y t2, and z t3, and then you integrate over x over y over z. The question?
Yeah. In this case, the integration of t, in the case of xn is 1.
Sorry?
Pxn is 1.
Ah, okay. I haven't finished. This will come. So I could continue and integrate the others. x1, x2, x3. And if I do this, and this, I will get a probability of less and less variables. At the end, I will get only one, which is what you get. At the end, it will come the third condition, that is called normalization. Which is the integral over dx, let me call it mu, or let me call it s, because mu I call it for different dimensions, s, of p xs ds. So let's say I continue integrating. At some point there will be only one variable and one time. This one. And now integrate over the last variable, xs. This must be 1. That's what is the same. At the very end, I will get 1. This is called normalization. If these three conditions are satisfied, this is for all NES. This is for NES. If these three conditions are satisfied, you have a stochastic process. So the stochastic process is completely well defined. So it's not that any P is valid. A P that is negative is not valid. A P that does not obey marginalization is not valid. And a P that is not normalized is not valid, so you should renormalize the process. Okay. Coming back to your question, if this 2 and 3 imply that if I integrate over all variables, so I take this, I integrate over dx1, I integrate over dx2, I integrate up to dxn of p, x1, p1.
Here is 1.
This is 1, exactly. x2, p2, xn, pn. This is equal to 1. So it's correctly normalized. Okay, this is what I would think the first. Let's normalize by summing all of them. But in the end, this comes from these two. You have these two, they imply this condition. This is also called normalization. And I think with this, I'm happy.
I don't know why I didn't learn these in the probability course. Now I'm learning.
I don't know, maybe they didn't explain this to you.
It's in Dr. Marcin's.
Yeah, I was completely lost. What are these integrals and what is this probability with a lot of variables?
That's why we are here in class, to discuss it.
I can very rapidly ask questions.
Yes. There's a question?
Yes. You say this is the process to verify if the stochastic process is well defined.
Yes.
That means if you want to study the process, we will get a sequence of values. At the end, we will check if the sequence we get is well defined.
Yes. Yes. But in principle, what you do is you define a model, a physical model. You define some rules in which it evolves, like the random walk. And most of the times, this will be satisfied. So this is a mathematical condition. So if you define a process in a very strange way, maybe this is not defined. But most of the examples that we use in physics obey this rule. Okay? This is just a mathematical condition of things are properly defined. Right? The point is if you say, okay, let me think about a very complicated process, I will define a probability density that is as I want, randomly, whatever I want. You put a very complicated function, exponential of the logarithm divided by the square root of the hyperbolic cosine. And then say, okay, does it obey this or not? Then if it doesn't, it's not a stochastic process. It's something you invented. But if you build the process from the physics, you define the rules and you go on and calculate the probability density, you will find this in most of the cases. Okay? Because this one is simple. You can always renormalize of distribution. This one is simple. You just must be positive. And this one is the most complicated one. In most of the cases, it works. This would be seen in examples, and you will see more. This is just very mathematical. In the end, I could have skipped this and go and explain you models. Right? Other questions? No? Okay, so we continue on Thursday then.